Oh, okay. Recording has been started. Let me share my screen. Mm, I hope it is visible, right? Okay. So let me minimize this one. Okay, so let's start. Okay. Good evening, everyone. So this is week 9 of the Introduction to Machine Learning course. Now, in week 8, if you have not attended week 8 we cover naive Bayes algorithm, an example of it, the Bayesian networks, and similarly an example, multi-class classification, multi-level classification, and their evaluation metrics like micro, macro, and weighted matrices like effort score or let's say precision recall, right? So in week 9 we'll be covering clustering algorithms mainly. So k-means, agglomerative or hierarchical clustering, then DB scan, and metrics to evaluate the quality of clusters like C-Loud score. And we like will also cover or touch upon like basic concepts of reinforcement today. So yeah, so that will be today's plan. Okay, and can anybody just confirm in chat whether I'm audible or not? Or just unmute and see.
Audible, sir.
Yeah, thank you. So, so okay. Uh, okay, so let's start with artisanal clustering methods like k-means. Okay, so k-means, so what is clustering first of all? Clustering is basically an unsupervised method of grouping data points. Okay, so for example, if I have data points, but I don't have labels, I want to just clusters based on their similarity. Some similarity metric, for example, a similarity metric would be, let's say, Euclidean distance, okay? Or any type of distance metric like Manhattan distance or anything, okay? So based on that distance metric or similarity score, we can cluster data points together and form kind of groups. Okay, groups are clusters between the data. So within one group, each data point will be similar. Okay, based on the distance metric we have used. Now, the k-means clustering is a kind of clustering method that works on by default it works on Euclidean distance. Now, so how it works basically? So you have a scatter of data points. Let's say 2D. Okay, x1 and x2 is the two features. Based on those two features, you want to cluster the points. Okay, so initially what we will do, we will randomly select 3 points as clustered heads or centroids. Okay, then based on that, select our like whichever points are closest. So basically we will assign all the points to its closest cluster head or centroid. then then basically compute the cluster heads again based on that that cluster we computed based on the initial centroid. Okay, so a good clustering method will be just take average between all the points of a particular cluster, then you have a new centroid. Okay, and basically repeat like point 2 and point 3 again until there is no change between the clusters. So that means there are no points that has been changed from the previous assignment to the next assignment. Okay, so let me give you a example of this. Let's just get some data. Okay, so, so we will not use real data. Instead, we just use we will source pivot. notebook. Okay, so we have week 9. Now what we are doing clustering, and for that we need for that, first of all we need data points, right, that are clusterable at least. So to get such data points, you can use sklearn dot pre-processing and basically data sets import make blobs. So make blobs, what it does, it can give you clustered data points based on your record. So basically, if I want make blobs, so what it expects how many samples you want, so how many data samples you want, how many dimensional data you want. So basically, n features equal to 2 means there will be 2 features for the data or 2-dimensional data. Okay, just like this this graph, just like this graph. Okay, so you can plot the data points into 2 dimensions. Can you just mute yourself? Okay, let me mute. Okay, just make sure that you are not unmuted if you're not speaking. Okay, okay. So it expects number of samples, number of features, and the centers, how many centers you want from the data. So let's just take these and the center box means the data points will be generated from -10 to +10 axis. So in x-axis -10 to +10, in y-axis -10 to +10. Okay, now let's just take these things. So it returns points, or let's say data comma cluster IDs. Okay, and let's say I want 2 clusters, or let's say I want 3 clusters, not 2. Okay, now what is this cluster standard deviation? And by this step we are basically generating data. It's not like we are doing any clustering at this point. We're just generating data for the clustering algorithms. So in real life, you would have real life data, right? That you will be clustering. So just for simulation or test, like for explanation purpose, I'm just generating synthetic data as per my requirement. So for example, I want 100 data samples, 2 features, so that we can plot easily in 2 dimension. And let's say I want 3 clusters, and cluster standard deviation 1 means from the center, the spread of the clusters will be controlled by this parameter cluster standard deviation. Okay, so we'll change everything and see how it will look if I change each parameter of it. Import matplotlib plot splt np. Okay, now we have data. So data is basically 100. So it's 100 samples. If I just check the shape of it, right, it's 100 comma 2. That means there are 100 samples of 2 feature size, right? And we have 3 centers, so we have to confirm that. So how we can confirm that? We can just do a scatter plot of the data, right? So to do that, we can just use plt.scatter. And for the x, we will pass data, all data points, the 0th axis, right? So the column, this column, 0th column, so it will be represented as the y points, sorry, x points, and then all points 1, y-axis. Okay, so these are the data points. So you can clearly see there are three clusters, right? You can visually confirm that, but let's not visually confirm it. Let's see what are the cluster IDs that are being generated. So these are the generated points cluster ID. So the first point, if I just print data, yeah. So this point belongs to the cluster ID 1. Okay. our next point belongs to cluster ID 2. The third point belongs to cluster ID 0, like this. Okay, so there are three clusters with 0, 1, and 2, three IDs. Now you can just color them. C is equal to cluster IDs, so it basically gets colored. So the cluster IDs becomes the color uh, of the scatter points. Okay, so we can uh, do plt dot legend. I don't think it will produce anything. Uh, anyway, so to in this case, the plt dot legend would not work. So to work with plt dot legends, what we have to do, we have to plot each cluster separately and then label them. Okay, so how we can do that? So just to, let's say, see which cluster is which ID, we can do something like this. Cluster index 0. Okay, so we just get uh, all the cluster data which has ID 0. How we can get that? So get all the points from the data where the cluster ID is equal to 0. Okay, similarly, you can just or you can just data 0. Okay, data 0. Then similarly, data 1 and data 2. Now we have three different clusters, right? We can similarly plot, and let's say color I can just name that my cluster 0 would be red and the label of that cluster 0 would be 0. Okay, in string. Now copy paste 3 times, put this 1, 2. For the second cluster, let's say blue, and the third cluster, let's say green. Okay, so now if I do plt.legend, oh sorry, cluster data 2. Yeah, now you can see red is this is the 0th cluster, this is the first cluster, and this is the second cluster. Okay, now we have a data that is well clustered, right? So we assume that we don't know these cluster IDs. We'll try to find it with the algorithms. So in real life, you would only have this data. So because we have created a synthetic data set, or right, that's why we have the cluster IDs also. But let's assume that let's just delete the cluster IDs. Okay, let's just not have the cluster IDs. Yeah, just we have just deleted it. So now if I just check cluster IDs, it's not there, right? The variable is not yet defined. So now we have the kind of real life data that we have only the data and we don't have any uh, like cluster IDs as such, right? Now let's go back to the slide. Okay, so first we will try k-means partitioning. So how it works, let's just revisit that once. So let me zoom here. See, so it basically marks three random points as centroids, three random points from the data. Okay, and then compute all the data, like the distance between all the data points. Okay, let's say from three centroids. So the k means how many number of clusters you want. So you have to predefine the number of clusters. So here the k means you pass as a parameter how many number of clusters there will be in the data. Okay, so let's say if the data, so because our data has three clusters, if I pass 2, maybe these 2 clusters will be considered as one cluster. Okay, so choosing for k-means clustering, choosing the right k is very important. So let's say I choose k as 3. So what it will do, it will randomly allocate 3 points as the cluster IDs, okay, as the cluster heads. and then compute which point belongs to which cluster. So it will basically compute distance between 3 points, 3 centroids, and assign to that particular centroid which has the closest distance. Okay, so let's say these are the assignments. Okay, so all these green points are assigned to this green, red points are assigned to this red, and the blue points are assigned here. Now to compute the next cluster heads, okay, or updated cluster heads, what we will do, from each group we will just take average. Okay, so maybe taking average from all these points would choose a new head here. Maybe it is not within that number set of data points. It is something else. It is entirely a separate data point we created. Let's say after averaging them, we have a point here. Okay, that becomes the new centroid or cluster head. Okay, like this here. Right here, after taking average, the centroid becomes here. The green one becomes here, and the blue one becomes here. Right now, we have new centroids. Again, compute the same assignments. So we compute where the data points will be assigned to which clusters, and see whether my previous assignment and the current assignment has changed or not. It's directly comparing whether the set the assignment we have in step 2 is same as step 4 or not. If it is same, my algorithm has converged. If it is changed, that means my algorithm has been improved, or my clustering has improved. So just continue with step 2 and step 3 again. So again, compute the centroids, right? New centroids, uh, check whether assignments are happening or not. New assignments are kind of changing or not. Okay, so we'll see here how to do k-means clustering, right? So from sklearn dot cluster, there should be k-means, k-means, right? Okay, k-means what it requires. See, it requires x means the data in clusters. How many clusters there will be? Sample weight. That means there can be instances where some part of the data you trust more than the other. In that case, sample weight will be the kind of variable you will be providing. Okay. Okay, and then maximum iteration is 300, means it will. So if it doesn't converge within 300 iteration, it will get stopped at 300, so that it doesn't run into an infinite loop. Okay, and just to uh, get reproducibility, right? You just do a random state initialization at the algorithm. For example, random state, let's keep it 42, and data is the x. Let's say I want 2 clusters. Just name number of clusters equal to 2. Okay, so what it returns? It returns the 2 centroids that are computed and the assignments. Okay, and this is something, I guess, C score or something. Let me clarify. Let me see what the third thing is. It returns centroid level and inertia float. That value inertia sum of the square distance. Okay, it's basically the kind of consistent. So it's a consistency metric of the clusters. Okay. Yeah. So sum of square distances to the closest centroid of all observation in the training set. Okay. So basically, if this is low, that means my clusters are consistent or very much mm, kind of close to the centroids. Data points are very close to the centroids. Okay. So it returns 3 values. One is centroids or cluster heads. Second is data assignments, or you can say cluster IDs. Cluster IDs. Earlier we had a cluster ID, right? Oh, okay. It will be better if we didn't remove it. Then we can cross check whether they are same or not. Anyway, It's not cross check. And another thing, that the inertia or some metric, okay. Okay. If I run centroids, okay, fine. So what are the centroids? So I pass number of clusters to be 2. Okay. So if I just go with this plot, currently we have 2 clusters. So cluster ID 0 and cluster ID 1. Cluster ID is 0 and 1. So data 0, data 1 becomes like this, and just copy this also. Yeah, and remove this one. So in my assignments currently, this entire block becomes cluster 0, and this block becomes cluster 1. And what are the centroids? If I just plot the centroids too, see, they might not belong to the set of data points. There might be some different value. Okay, it's basically taking average between currently assigned cluster points. So plt dot centroid scatter centroids all points 0, centroids all point 1. So there basically we are plotting 2 points, right? Cluster 0, cluster 1. Marker, let's keep marker as star. Marker size to be, let's say, 50. Okay, and color or C equal to, let's say, yellow. What is the error? Marker size S. That should be S, not marker size S. Yeah. So oh, sorry. It will be comma. Yeah. See, one cluster is here, second cluster is here. Let me bring the size up and also do a EC is equal to K. Yeah. Now see into 200. Yeah. So one cluster ID is here, second cluster ID is here. It is not within the set. It may or may not within the set of data points, right? So for example, here it is very close to it, close to these 2 data points, but here it is completely outside or basically within these 2 subclusters, right? Now let's choose number of clusters to be 3. Okay. Now what will be changed? We have another cluster ID now, 2. Just copy this line. Oh. Now see, we have 3 cluster IDs. One here, one here, and third one is here. And the assignments you can see by color, right? So this is the cluster 0, this is cluster 1, and this is cluster 2. Okay. Okay. So any questions still came in at this point? Okay. So one thing that should come in your mind that, okay, so not always the data will be 2-dimensional, right? So in most of the cases, my data will be multi-dimensional. Right? Let's say 6-dimensional, 10-dimensional data. And now I cannot always plot 10-dimensional data. Let's say I can always do TSNE or PCA that would reduce my dimension to 2, which is kind of plottable, right? However, that reduces the separability and all. So I cannot surely say, okay, how many clusters are there based on then cluster my data, right? So I cannot always visually confirm how many clusters are there in a data. Okay. So what is a better approach? So the better approach would be to go with a consistency metric like seal out score. So seal out score, what it does, it computes like with a current allocation of cluster IDs, like how correct it is based on the current data. Okay, so basically um, the metric that is getting returned here, right? This one is similar to seal out score. So seal out score basically gives you. So I can just refer to the slide here. Yeah, seal out score basically gives you cluster consistency. Okay, whether the clusters are consistent with the assigned IDs or not. Okay, so how to compute seal out score? There is so from sklearn. So they it's in the metrics library. Okay, metrics import seal out score. Yeah. So let's see what it represents. If we zoomed in a bit, seal out score, right? So it takes data and the corresponding labels. Labels means the cluster IDs that you have computed from any clustering algorithm or somewhere. Okay. Now, what it returns mean seal out coefficient of all samples. So basically, whether the assignments are consistent, what is the mean kind of mean response to that? So, compute zero coefficient calculated using mean intra-cluster distance. Okay. Now, let's compute. Let's data. We have data and we have cluster IDs. Cluster IDs will be the labels in this case. So X labels, right? Yeah, this is my seal out score 0.656. Now, if I have two clusters, let's see whether my score would have changed or not. So if I have two clusters, now I have the new center IDs. I will just call this one on top of here. Now, for this one, we have only two clusters. This one we have correctly computed as three clusters, right? Yeah, see my seal out score is actually bigger, right? So it's basically an kind of minimization objective that we will have. And let's say if I have, and there is a catch also, so it's not entirely minimization. So if I have four clusters, so my data has only three valid clusters, right? But if I have four clusters in my, then yeah, here four clusters, see my score again reduces, right? So this is a catch here. So so anyway, the seal out score would be reducing if I am increasing the number of clusters. So what is the optimal number of clusters? That's the question, right? Where I should stop. So the method that we usually follow is it's called elbow method. Okay. So we basically took wherever this elbow starts here. So after we have a see, this is kind of an elbow, right? Here we would have the optimal number of clusters. So so it's basically a kind of mm, like brute force approach. You go with all possible clusters and see where this elbow breaks. Okay. So in this break, so this is the kind of optimal cluster you have. So let's do it. Let's do this for this data, right? Uh, we have this data. So this is elbow, the elbow method for determining optimal number of clusters. So what we have to do, we have to loop from two cluster to uh, let's say 10 clustered. Okay. So there is always a kind of upper bound that you can choose based on domain knowledge. So you know that, okay, my data point has 10 different kind of possibly would have 10 different kind of grouping. So I will stop at, let's say, 15. If it has more, then I can just may kind of consider that one too, right? So let's see, if I have 11 splits, then I would have considered it within 15, right? So let's for this data point, we know that it is optimally clustered at three clusters and three clusters, right? So let's stop at 10. So we'll loop from 2 to 10 and see where my elbow breaks. Okay. So possible clusters are for possible cluster in range 2 to 11. That means 2 to 10, right? We will do k-means. K-means on the data with possible clusters. Compute chill out. Chill out score, and then just do append. Chill out score. Let's keep a list and append it. Done, right? So it looped for 10 to 10. That means I guess nine times, right? 2 to 10. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9 times. And chill out. This is the kind of scores we get. So plt dot plot. Yeah, see, in 3 we have the break, right? No, possibly within 3 and 4. Okay. So because see this data point. Yeah. So within 3 and 4 we have a kind of split. So the first break that we have here. Okay, so whenever we have this type of elbow type slope here, if we just zoom in here, see, this would be my optimal cluster 3. Now let's build another data with, let's say, 5 samples, 5, and let's increase our data samples to be 200. Now we have, sorry, 5 centroids. Okay, 5 centers. If I just plot my data, cluster IDs. Yeah, so the data looks like this. Okay, 1, 2, 3, 4, 5, 5 clusters. Now, if I compute chill out, so by chill out score, I can see it is giving us 6, right? So this is not an elbow. This is an elbow, right? So we get 6. So because the clusters are so overlapped here, maybe it is getting confused at this stage and kind of considering 6 clusters. One may be this one may be this one, and third may be, yeah, the sixth may be this one. Okay. So what we can do, yeah. So it's very close, right? So my clusters are 5. We have 6 clusters from next, the optimal clusters to be 6 from Silhout. And let's see what is the assignment. Then we will be kind of sure, right? Where it finds the 6th cluster. So if it is 6, yeah, see, here it finds the 6th cluster, right? So 1, 2, 3, 4, 6, 5 and 6th. Okay, so it's very close, right? It has some error, obviously, based on the noise distribution of the clusters, whether they are overlapping or whether they're, let's say, very much uh, uh, they separated. Based on that, the seal out would be different. So let's just create very separable kind of seal outs, right? So so how I can control the separation from this from this make blob function by reducing the cluster standard deviation, right? So I can just reduce the cluster standard deviation to 0.5, which will kind of control the spread of the clusters. So they will be more packed. Okay. See now, no, here the data points are very close. What other thing I can do? Oh, okay. I can also okay. I can also specify the centroids by this. So I can either specify how many centroids I want, or I can specify the exact centroids that I need. Okay. So just try a different random seed. Yeah. See now the centroid, like now the clusters are very much well separated, right? So now let's see what is the seal out, or how does it look. So for the overlapping cluster, it kind of overestimates one cluster, right? So it instead of 5, it gives 6. So now for 5 well separable clusters, okay, so here it is very difficult. So the elbow is very tiny. Okay, so the fifth, let me do one thing. So on the fifth one, there is like I cannot see it even, right? But there is a slight elbow there. Okay, we cannot see it by eye. But anyway, you get the point, right? But there, like at the first view, see this is somewhat like kind of upward, right? And this is somewhat downward. So there will be a kind of elbow here. Let's try on different cluster set. Let's increase the cluster centroids. Okay. Now this one, let's see. I just wanted to get a good case. Oh, here also it kind of overshoots and decide it's 5. Okay. So no, it decided it's 6. So yeah, so here it kind of gives 2 clusters. So you can kind of see that with the seal out method, uh, without even kind of uh, visually confirming how many clusters there are, we can approximately guess, okay, there are like within a factor of 1 or 2, we can guess, okay, there's a p number of clusters. Okay. So so for 2-dimensional data, it is not that much obvious. But for, let's say, if I have higher dimensional data, right? If I have 10-dimensional data, then I cannot possibly visualize it in 2 dimension. Okay. So in that case, the seal out method is the method that we go for. Okay. Fine. And you basically check for this type of a elbow. Whenever you find this elbow, you just and so that then you stop. You stop there. Okay. K means is done. So in K means you have to pass this K value. That's why you need that seal out score and all. Now for hierarchical clustering, the method is simple. You basically group from, let's say, so something like this. Let's say into 2D space, the points lies in this kind of configuration A, B, C, D, E, and F. Now, because B, C is closer, we just combine them to one cluster, and then DE is closer, combine them to another cluster. With the DE cluster, F is closer, so combine DEF. Then these two clusters are closer, so combine BCDEF, and then you combine with A. So this basically kind of give you a thematic grouping. So based on, let's say distance, cosine similarity, or anything. Okay, any distance metric. Okay, so it gives you kind of a tree structure. So let's see how we can implement it in the same data. So I have the data like this data. Now I want this agglomerative clustering, right? So from scalar dot cluster import agglomerative clustering. So it is basically an bottom up approach, something that is shown in the slide. So bottom up. So it should be I think this. Okay, so it's a bottom up approach. Decisive is just opposite, so it's from the top down approach. Okay, so agglomerative clustering, just add more cells. Okay, here also I have to specify at which level I should stop clustering. Okay, so if I just say, okay, stop at whenever you have two clusters, it will basically keep clustering until it has two clusters and then stop there. Okay, if I just say a number of clusters to be one, it will cluster to the root node. Okay, so to here, it will cluster till here. So let's say I want uh, two clusters, so it will basically stop. So no, here how many clusters we have? 1, 2, 3, 4, right? Now if I want two clusters, it will stop here, 1 and 2. Okay, if I want three clusters, it will stop 1, 2, 3. No, 1, 2, 3, 4. So whatever is the closest that you can get. Okay, so let's see. I want number of clusters to be, let's say 3. Okay, so currently we have 1, 2, 3, 4, 5 clusters. I want 3 clusters. And any other thing that they want? No, this affinity, these things are not that much necessary. Metric you can change. So by default, the metric is Euclidean. Yeah, by default it is Euclidean. Okay, but you can change it to Manhattan, cosine similarity, any other metric of your like. Okay. So here I can see CLS clustering, CLS dot fit. Or let's just do fit predict. Okay, fit predict. So where basically we are doing a fitting, and then we are just getting the cluster IDs. Okay, so it returns the cluster labels. So y will not will not give. It is not used. It is ignored, right? So because this fit predict all these APIs basically have this y. Uh, that's why they have kept it, but it is not used. Okay. So data. These are the cluster IDs we have. Now, if I just plot them, just mark these two. So we have three clusters. Cluster ID, cluster IDs. We don't get centroids in this case, right? So it's not possible, not given. Yeah. So this is the kind of clustering we have. So all these three clusters are currently considered as one. Then these two as two. Okay. Now let's increase the number of hierarchical clusters. A similar thing, you can also to go with seal out and then choose the number of clusters here. Okay, 4. Then my cluster would be, let's not use this graph. Let's use the previous graph here, this graph. Yeah, so if I choose 4, then these are the 1, 2, 3, and this one is the 4th. Okay, similarly, if I do 5, now we have 5 clusters, right? If I do 6, see, same here, there is kind of a breakup between this entire cluster into 2 clusters. Okay, so 5 is the optimal. Let's keep 5. Okay, so now if I just see what is the kind of this grouping, right? We can also plot it. I guess there was a code. Wait, let me find it. So it is uh, agglomerative. Sorry, agglomerative clustering. Yeah, I want to you kind of do this graph. Okay, let's see. I guess here we'll have it. Nope. Wait. Yeah. Yeah. With this, we can plot data we have. X will be my data. Yeah, this is the kind of grouping we have. So metric is Euclidean. Method Then, okay. So this word method, that is something, wait, median anyway. Okay, so this is the kind of clustering we have. So if I want 5 clusters, my cut will be here, 1, 2, 3, 4, 5. Okay. If I want 2 clusters, my cut will be here, 1 and 2. If I want 3 clusters, my cut will be one kind of here. So 1, 2, 3. This 1, 2, and this level 3. Okay. Okay. So, and lastly, we have, so these are the kind of 2 clustering methods. And lastly, we have density based clustering. So in this case, we don't have to mention any number of clusters. Rather, the clusters are formed based on data points density. So where the density is more, the clusters will be forming surrounding that area. Okay. And one good thing is, see, these other 2 clustering method doesn't have a noise cluster, right? So whatever noisy data you have, it will be always assigned to a valid cluster. But let's say you would always have, in real world, you would always have noisy data points. Okay. So for example, if I'm clustering sensor data, or let's say clustering any human parameters, let's say biomarkers or something, right? There will be always data points that are out of distribution, that stays beyond that mu plus minus 3 standard deviation range. Okay. So beyond that 97.7 percentile, uh, there are always data points which are assigned to valid clusters. Okay, that makes the clusters noisy. So that is hard to deal with in k-means or hierarchical clustering. However, in density-based clustering, there is a default cluster with cluster ID 0, that is known as the noise cluster, noise cluster. So whatever points gets assigned to cluster ID 0 are considered as noise. Okay, so it can basically save us from noisy data points from sensor data or any real world data. So sometimes in for example, in my domain, so whenever, let's say, I'm doing a clustering, I don't know how many data points, how many clusters there will be, and there is a noise component within the data points, then I use dbscan. Okay, so let's see. So frame from sklearn dot cluster import dbscan. Okay. And now dbscan, what it expects you to give, it expects you that epsilon parameter between, so that epsilon parameter between, where is the slide? Yeah, between two neighboring points. So okay, I know that 2 data points will be similar based on Euclidean if their epsilon is within 0.01. Okay, that means they are very close in the space, in the like embedding space, right? Whatever the dimension may be, let's say 2 dimensions. So it's in 2 dimensions. If my 2 data points are closer than 1 meter, that means they are almost same. Okay, or if they are closer to 1 7, based on the scale, obviously. So it don't take domain knowledge is also important for dbscan. However, let's say if I know that like within less than 1 meter, it is, if the points are similar, then I can pass epsilon to be 1 meter. Okay, for our case, the data is actually -10 to +10, and in x-axis, and also -10 to +10 in the y-axis, right? So let's say if 2 data points are within 0.5 of each other, then that is the epsilon of considering both of them to be similar. Okay, so we'll say EPS, what we have to do. It's already by default it is 0.05. right? And there is also this mean samples thing, and mean samples, I guess it is also available for the hierarchical one. Here, is it? Okay, anyway, mean samples is not there, but here we have this minimum samples thing. Yeah, it's not there in the hierarchical one because that doesn't deal with noisy data, right? This one deals with noisy data. So whenever, let's say, a cluster is there with less than the minimum number of sample data points, it will be assigned to the noise cluster. Okay. So the entire that 4, so if the minimum sample is 5 and the number of points in a particular cluster is 4, that entire 4 points will be assigned to the noisy cluster N, which is a cluster ID 0 for this case. So let's the distance, let's keep it Euclidean. So epsilon 0.5 and number of samples to be 5, let's say. This is my db scan. You scan fit predict on data will give you cluster IDs. Yeah, sample weight, everything. Sample weight you can always use if you just trust some part of your data more than the other one, then the sample weight would be useful. Why is not used? Now cluster IDs, I can use this plot. This is the clustered it form. So maybe we have to reduce the number of reduce epsilon. So what are the number of clusters we have? Let's see. Cluster IDs. So basically we have to increase the epsilon. So it's basically the epsilon is very close. So for two neighboring points to be similar, 0.5 is very small in this case. So you have to maybe make it to 1.5. I'm just guessing it. Okay, at this point. Yeah, now it makes sense, right? So 1.5. So this epsilon parameter is basically a hyperparameter that you tune. Okay, and it's basically dependent on the domain knowledge you have. So for example, in let's say one of our studies, we cluster radar data with this, so point cloud of like the radars. So in that case, we know that okay, the scale is in meters, so we keep it within 2 meters. So if 2 points are not exactly 2 meters, I guess it was 1 meter. Okay, so if the 2 points are within 1 meter, then they are belong to one same same cluster. Okay, similar to that. So the domain knowledge is important. So for our synthetic data, the scale is -10 to +10, right? So in that case, a epsilon value of 1.5 is good enough. So what are these blue clusters? So these are basically assigned to noise point, like noise cluster. So if I just see cluster IDs, see this -1 cluster, this is the noise cluster. So there are valid clusters 0, 1, 2, 3, 4, 5 valid clusters, and then this -1 cluster represents the noisy points, which are far out from the initial cluster. So see, for example, this point, right? It is far from the actual cluster. Okay. Similarly, these points, these are very far ahead from far away from the actual cluster. So that's why they are marked as noisy points. Okay. Okay. So what happens if I increase epsilon more? So if I increase, let's say, to 3, right? Yeah, so these two clusters become one, and there are no noisy points because now within three units, these points are also fall within 3 units, right? And because these two clusters fall within 3 units, they are considered as one. So see, if I just see the cluster IDs, there is no -1, right? So there is no noisy cluster. So choosing this epsilon parameter is very important for like important as per the domain, right? If I just want to have 5 clusters, I would have to choose epsilon to be 1.5 in this case. Okay. Okay, so this is what DB scan looks like. Okay, and for example, I can show you one quick. Let me show you one quick example of it. Uh, you slash here, right, in this video. Um, here. Here, you see, this is kind of an use case of DB scan when DB scan is used for sensor data. See, these are the kind of centroids we are tracking. Okay, and this is the entire clusters that are moving. Okay, and the algorithm is very fast, so we can uh, run it on in real time. See this? Okay, it's fine, right? Okay, so density-based clustering is also done. Chill-out score we discussed. Okay, now we have more time, so we'll dig into reinforcement learning now. So, so these topics are from week 12, obviously, but we will cover these parts too later on, maybe. Okay, but we'll just like start with reinforcement because this is like up till this TD learning part. This is quite a bit theory there. Okay, so we'll just touch upon and like start learning or start doing reinforcement learning from basics ones, like from this week. Okay, and GMM expectation minimization will just cover in the incoming weeks. Okay, so this is kind of an exciting part at this point. So I guess you remember what we defined reinforcement learning to be in the first class, right? So let's just go to that slide once. Week 1. So yeah, week 1. No, we defined it in week 2, not in week 1, week 2. Yeah, here. So reinforcement learning is basically, did we write any definition for it or we just wrote some examples? Here, right? So you can see the picture too. So there is this environment, real world environment, and then there is an agent that takes some action on the environment. For example, here, right, a mouse uh, trying to solve a maze and find out this piece of cheese. Okay, and so the mouse itself in his head, in the mouse's head, there is a kind of state representation, right? How he perceived the world. So how it is the state representation of the mouse, how it is different from the real state, right? So for example, um, let's say I'm sitting in a room, right, but I am staring at this laptop, so my current viewport or my FOV, right, that is only at the laptop. I cannot see what is happening, let's say, in behind me, right? So even though the world has that information, okay, whatever is happening behind me, that is part of the world, but I cannot perceive it because I am currently viewing at the forward direction, right? So that is my state. So my brain has a state which covers a kind of a part of the world, right? Basically, it covers a subset of the world. Okay, so the environment has this global a kind of state that gets observed by the agent or something like a mouse or us, right? We act as an agent. Based on that, state or state representation in the agent's head, uh, it takes action, it takes something. So for example, the mouse can choose to move left or right, or go forward or go backward, right? So these actions it took on the environment, or let's say based on that action, it perceives a different part of the world. So for example, if I just look left, right? So I don't perceive the laptop, I perceive the left side of me, right? So my current state in my head has changed. So I cannot see what is happening on the laptop, but I can see what is happening in the left side of me, right? So that's the kind of action impact on the state. So based on the action, the state changes. Okay, the world remains same. Okay, but the state representation or whatever the agent perceived from the environment, that gets changed. Okay, and also let's say if something amusing is happening on my left side, then let's say I would have a positive reward, right? So for example, let's say some monkey is playing on the right side, left side, then I will just laugh, right? So that basically gives a positive reward. Or something bad happening, then I will be negatively rewarded, right? So for example, for a mouse scenario, if it finds the cheese, that's the positive reward. If it doesn't find the cheese, that's a negative reward. So there are. So what is the example that we decided on the second class? Reinforcement learning, learning to ride a bike or cycle. Okay, so the world is road. The state of the agent is which part of the road he is currently observing. The action is whether he's pedaling or steering the bike, and the reward is whether he's still riding the bike or bicycle, or whether he has fallen from it, right? So if he is still riding, then it is a positive reward. If it is if the agent has fallen from the bike or cycle, then it's negative reward. Okay. So where is the yeah here. So this is the kind of generic diagram that explains the interaction between the environment and the agent. So the agent takes an action based on that. No. So it's kind of an it looks like an so what happens first? It observes state and then took action, or take action and then observe state, right? So basically this state is observed first. So you cannot take action without perceiving the world, right? So you take action at t0. I sorry, you perceive the state of the environment at s0 or t0, that is s0, and then you take action a0 based on that state. You get reward r0, and the environment transition, or basically in your head, maybe the environment is still the same. Okay, so whatever you do, the world doesn't get changed, right? You just perceive a different part of it. So that means your state representation st changed. St plus 1, it becomes st plus 1, and then you basically take another action at and get a reward rt, right? Something like this. This is the entire agent environment interaction of reinforcement. Okay, so so today what we will just contain our discussion within how we can represent a world, or what type of worlds are there in reinforcement literature. Okay, so there are mainly three. So there are other worlds too, like let's say I can just name their initials. So for example, there are non-Markovian worlds. Okay, partially observable Markovian worlds like this. It's a partial observable and non-Markovian. So there are many types of world representation. So world means how we can model the environment. Okay, based on that, the entire interaction would get changed. So what are the primary types? Let's just name them. So these are Markov Processes. Okay. Then we have Markov Reward Processes. Then we have Markov Decision Process. And we just keep our discussion to Markov Decision Process today. Okay. Because this is the part that is covered in the course up till here. So the maximum thing that is taught in this class is in this course is this TD learning thing, right? This TD learning, temporal difference learning. So this assumes the world to be a Markov decision process. So you have to know Markov process, Markov reward process, and Markov decision process to know the part that is covered in this course. Okay, so we'll see. So let me just connect my tablet, and we'll see. But by the way, any questions you have from the clustering part? Okay, so let me just connect the tablet and drink some water. Okay. না হচ্ছে জল খেতে পারি।
I have a doubt, sir. Hello.
Okay. Let me just create another page. Okay. So we have Markov processes first. So what are Markov processes? An example would be gas. Okay. So any gas, uh, let's say carbon dioxide, okay, or something like nitrogen dioxide, carbon dioxide, anything, right? You can consider them to be Markov processes. So what I mean by Markov processes, they basically change their state. They don't get influenced from external entities like agents. They continuously change their state from let's say ST to ST plus 1 without the influence of an external entity, and doesn't produce anything as a result of it. So it doesn't produce any kind of reward. Okay, and it doesn't produce anything per se. So and state can be represented as, let's say, density and volume. Okay, so a gas, let's say S0, it started, we just, let's say, put some nitrogen dioxide gas in the air and then measure it density and volume at some instance. Then at the next state, it transition, or it basically spreads, right? So it transition to state 1, spreads a little. Again, at the next time, so time here we consider time as discrete. Okay, so it starts from T0, then it starts next transition, it transition to T1, then it transition to T2 like this. Okay, so here the time is discrete. So our at which rate we will observe the state of the system or the Markov process is also discrete, right? So we basically start with S0, then in the time step 1 we have S1, time step 2 we have S2, S3, dot dot dot, like this. Okay, so how we can represent it? So Markov process is basically, so what are the two things that are there? So one is this set of states, right? Set of possible states, and another is this transition. However, is represented by, like, whatever is represented by this transition, right? There should be something that help it transition from one state to other. So a Markov process is represented with only two things. One is this set of states S. So S is equal to the set of states S0, S1, dot dot dot, Sn, and we consider finite number of states. Okay, so there can be, let's say, 5 states, S0 to S4. Okay, and they transition between themselves, which is not true for gas. Obviously, there can be infinite number of possible states for a gas, right? But let's consider it has finite number of states. And the transition matrix that is known as P. So probability of transitioning from one state to the other. So basically, it's an S cross S matrix that represents probability from S0 to S1. What is the probability of transitioning, right? So it is represented like this. Let's say there are 3 states. Let's say n is equal to 3. N is equal to 3. So we have, if I count from 0, it is Sn minus 1 is the number of states. So Sn minus 1 is the last state, right? So S0, S1, S2, and then in this axis also you have S0, S1, S2, right? And all these values represent probabilities. And what is the property here? So from one state, you can only transition to 3 possible states. So you can transition to S0. So if I just do an this automata, right? So you can just write a NFA of this. So S0, S1, sorry, S1, and then S2. So you can transition to S0, or you can transition to S1, you can transition to S2. From S1, you can transition to S1, you can transition to S0, or you can transition to S2. From S2 also, you can transition to S2, or you can transition to the previous state. Okay, and there is always this start state. Okay, so there should be this S0 should be, let's say, the start state. So what is the property of this P matrix? It is an S cross S matrix, and this rows and columns, they sums up to 1, right? So this rows sums up to 1, as the columns also sums up to 1. Okay, so if I just sum them, these values, these values would be 1. So a valid confusion, so a valid transition probability matrix would be 0.2, let's say 0.3, 0.5, 0.7, 0.15, 0.15, and let's say here we have 0.4, 0.3, 0.3. So you see here, yeah, the columns might not sum up to 1. Okay, only the rows, because it represents from S0 to S1 what is the transition probability, from S0 to S1, from S0 to S2. Similarly, from S1 to S2, something like this. So only the rows would sums up to 1. Okay, now, okay, so up till this is a kind of a theoretical concept, right? So what about how to implement it in code? So let's implement a 3-state Markov process in code and see what is the kind of uh, like the sequence of states you observed. If I just let it unfold for let's say 10 timestamps. Okay, and why am I mentioning timestamp? Because time is considered as discrete, as I mentioned earlier, right? So the time is considered discrete, so each instance we call it as a timestamp. T0, T1, T2 up till let's say T9 is the 10 timestamps. We'll just implement it shortly. But now, what is the transition? How the transition happens in code? Let's say my Markov process model starts at S0. So we represent it as a probability. Okay. So the the state model is represented as a kind of probability. So S0, S1, S2. Currently it is in, let's say, S0. So if I just put the probabilities here, where I can find my Markov process, what is it? It is 1, 0, 0, right? So so if I just observe, I will definitely find it in S0. Similarly, if it is in S1, I kind of your I'll observe it like this probability, like 0, 1, 0. And if it is in the second state, I will observe it as to be 0, 0, 1. So this state represents S0 state. If it is like this, it represents S1, and if it is like this, it is representing S2. Okay, now so what I have to slice here. See, if I am transitioning from S0, I need to slice this row, right? And then just do probabilistic sampling to get to the next state. So I have probability of transition to S0 with 20% probability, with 30% to S1, and with 50% to S2. So from S0, I have to get this row, this probability row, right? So what I can multiply it with? See, 0.2, 0.3, 0.5, 0.7, 0.15, 0.15, 0.4, 0.3, 0.3. Okay. Sorry. Let's say I'm on S0. Okay. So it will be 1, 0, 0. I just transpose the row vector. Okay. So now if I just multiply it, see what will happen. It will be this one plus no. So I will just keep it as a row. Right? Let me. I was not. Like we cannot multiply it with the column vector. We have to multiply it with the row vector itself. So 1, 0, 0. So how it will multiply? Here, here, here. Then the second part would be here, here, here. This is standard matrix multiplication, right? Third part would be here, here, here. Right. So the resultant would be a column vector, a row vector of 0 0.2, 0 0.3, 0 0.5. Right? You get the point, right? So you just multiplied the state probability. This basically uh, you are at S0. So S0 would have 1, and the transition probability matrix P S cross S, you get the next state transition probabilities. Now you took just sample with these probabilities. Let's say you sample and get S3, right? So the next sample from this probability distribution would be 0, 0, 1. Now the question is how to sample, right? So in so sample you do something like this. So you just so this is the probability mass function, right? So how to sample? It's like general statistics. From probabilities mass function, you get probability like density function and just get a number from 0 to 1, right? Where in which bin you are in, you are at that state. So basically you do like this. So this is the PMF. If you just compute the probability uh, probability mass cumulative distribution function, not the probability density function. PDF is for the continuous distribution, right? So from PMF you just use CDF. Okay. Now CDF would be like this. So 0.2, the height will be 0.2. Then here you have height to be 0.5, the entire height. Okay. So the step is 0.3, and then you have 0.5. This is 1, right? So yeah. So here you have state 2, state 1, state 0. Now you generate a number and see in which part you are currently in. So if I just generate a number between uh, let's say here, right? Let's say I generate a number between here. So I hit this bin, right? Whatever the smallest bin you hit. So you hit this bin, so you are at state 2. If I generate a number here, right? I hit the smallest bin to be bin 1, so I am at state 1. If I generate a number here, I hit the smallest bin to be here, I generate a like state 0. So in code it is implemented like this. So if so just create a random number first in p dot random dot random, that would give you a number between 0 to 1. Okay. Now if it is, if the number, let's say r, right? If the r is greater than 0, less than the first probability p1, right? You transition to state 1, sorry, state 0. and if it is greater than p, less p1 less than the p2, sorry, just index them with 0, then you are in the first one, and if the r is greater than p1 less than p2, then you are at state 2. So this is the kind of sampling you are, the same as this. So you generate in which range, based on that you are transitioning to the next state. So what does it signify? So basically, let's say this is 0.2, right? So there is a 20% chance that, and this np random function give you a like uniform distribution. Okay, so within 0 to 1, there is the kind of uniform chance that the number would get generated at any point. Okay, so there is this 20% chance, that my number would be generated within 0 to 0.2. Okay, and then there is this, if this is 0.3, right? Sorry, yeah, 0.3, and this is wait, we have written it wrongly. So this is 0, 0.2, yeah, and this should be plus p0, and this should be plus p1 plus p0, this part, right? CDF part. So here it becomes 0.5, and this one is 0.2, right? So it has kind of 30% chance, of getting generated within this range. And then here it is p0 plus p1, right? So here it has how much? This is 0.5, and this entire sum becomes 1. So total we have 50% chance that my points would get generated in this range. Okay, so basically you just do the CDF computation as you go. So from 0 to first step, from first step to the second step, from second step to the last step. Okay, and then based on the transition, you generate the one hot encoding. So if it is, let's say if my R is generated as 0.9, my transition would be at state 2. So the next state transition would be 001. Okay, so let's implement it and see for 10th timestamp how, like, what is the kind of transition we are seeing. So we are currently implementing Markov processes, Markov, and we just use the same. And by the way, there is this good library that I built earlier. We'll maybe cover it a bit. So there are algorithms that you can try with this library. Yeah, so this library is there that I have built earlier to represent a grid world. So there is this target cheesecake there and a mouse there. You can try out reinforcement algorithm with it and see what is the kind of solution strategy that you are observing. Okay, so whatever you are learning currently is the building block of kind of how this game world is designed and all. Okay, what are the transition uh, available or possible? These are all kind of building blocks. Okay, so Markov process. So we have to define the starting state S0 to be np dot array, let's say first state 0 1 0. Okay, and then we have the state uh, set of states. Set of states are a set not a state basically, and list of all possible states. So 1, and then you have the second state. Finally, you have the third state, right? And then you have the transition probability matrix P. And what is it? It is a kind of 2D array, right? So, and because there are 3 states. Mhm. And what are the probabilities? 0.2, 0.3, 0.5, right? Here we have 0.7, 0.15, 0.15, and finally we have 0.4, 0.3, 0.3, sorry, 0.3, 0.3. Okay, so this is my transition probability. So this is how you, so what does it say? Okay, here, comma, say for here also. Okay, now we have properly formatted it. So P is a 2 cross the 3 cross 3 transition probability matrix. S, we have the set of states. We have the current state S0, right? Now the next state. So what is the transition equation? So define the transition, and these are important. So these are directly, so reward process and decision process are direct, like basically addition to this concept. Okay, so transition is what? I pass the current state is current. I pass the transition probability matrix. Okay, sometimes it is also written as PSS. Okay, so PSS, let's say, because it's PS2S, or we can write it PX SXS. Okay, just to, yeah. Now what will be the kind of transition? We multiply, right? So np dot matmul, the matrix multiply the current state and the PSS, right? You get the next state probabilities, right? So next prob. Now you use the Python sample function. So np dot random sample. So what I showed here, right? This is the kind of logic that it use. Okay, in like it just create the CDF and see in which step you are in. Based on that, kind of gives the next transition. Okay, so what you will do, random dot sample. See here, so random choice, not sample, choice. Yeah, so we have this possible selections. Size means how many states I should choose, right? I have only one, so I would choose the next state, right? The size would be 1. Replace equal to true. Replace equal to true only have, like, only it is only valid if I am choosing multiple things. Okay, and the P is the probability distribution. So next probability distribution. So it's basically you can that thing, sample with replacement, without replacement, that part. Okay, so my choice is how much the entire state space. Yes, and then the size would be 1. If I just don't pass the size, it will be default 1. Okay, and then replace equal to true, it is not valid for sample size equal to 1, right? It is only valid if my sample size is more than 1. Then if I am replacing, then there is a chance that I will pick up the same thing again, right? Okay, now lastly, P is equal to the next probability distribution. Next probability distribution of choosing between the states. So this is the next state, or S next. Let's return it. Now am I for T, Ti, in range 0 to 10, right? So there are 10 transitions I am considering. My current state P is current, right? Then I am transitioning. So S next is equal to transition S current, comma PSXS. Right now my next state becomes my current state, right? In the next loop, my next state becomes my current state. So my next state would be copied to my current state. Got it? So unrolling Markov process /n/n, and then your current state is this current state would be this. If I just unroll, S current is not defined. Why? S current, oh, S current is not defined. So initially my S current would be S0. If I just run C, must be in one dimensional. Okay, got it. So my states are what? This is state 0, state 1, and state 2. So this random choice function doesn't take this type of input. It takes 0, 1, and 2. And based on that, let's say my next state becomes 0, 1, or 2. Next state index actually is next index. From S, I just part the next state index. Done. So this is the transition. So it's transition from S0 to S0 again, then S2, then S0 again, then S2, then S0, then S0, then S1, S0, S1. So this is the transition. Okay. So this is how you implement Markov process. Okay, and this is how the transition probability matrix is defined and how the transition happens. Now let me just connect the charger, otherwise my laptop will die. Wait. Uh, okay, so next it is Markov reward processes. So what are those? So only thing that would change here is each state would have a reward associated with it. So let's say state 0 would have a +1. So for example, right? Uh, so a good Markov reward process example can be gases that change color, right? So So for example, if I compress a gas too much, let's say it becomes brown. Okay, if I just leave it, right, it becomes lighter and lighter. Maybe let's transition to yellow and then uh, orange, right? Something like this, or orange to yellow to white, something, this transitions, right? So each state would also have a associated reward or something associated with it that gives it a meaning. Okay, whether the state is good or bad or something like this. Okay, so reward process, it has the states has associated reward values. So whether the state is good or bad, we cannot directly tell whether the state is good or bad, but the reward will kind of give us a hint. Okay, so only change for the Markov descent like reward process, we just keep everything as it is, have a reward array, some same as, so reward is defined per state. Okay, per state, or sometime it is also defined per state action pair. Okay, so for simplicity we can just assume that it is defined per state. So for S0, let's say the reward is -1. For S1 the reward is, let's say, 10. For S2 the reward is, let's say, 2. Okay, and that is the immediate reward. So whenever you transition to that state, that reward gets like kind of emitted. Okay, so similar thing, transition, everything looks same. Now the transition not only gives you the state, next state, it also gives you the next reward. Okay, so the current state, you give the current state, the transition probability matrix is there, and you just move to the next state and you get some reward. That is Markov reward process. So that it's very intuitive. Okay, so reward gets associated. Now this would also give you reward. So it's give you next reward and current next state and current reward you get. Okay, so next state, and let's say the reward you get are RWD. Okay, initially so you will only get reward, you would only get reward if after transitioning. So initially my reward is, let's say, R is equal to 0, RWD is equal to 0. Okay, then you get some reward after you transition. Let's say RWD total is equal to 0. So current state is this. And initially you don't have any reward. You transition to the state. Reward, and you also add this value to the total reward. Let's say RWD total plus is equal to the reward. And after you, let's say, loop to 10 steps, right? So print total reward, RWD total at the end of 10 transition, the total reward. Okay. What is the problem? P must be one dimensional. Where? P must be one dimensional. So transition, then random choice. P is one dimensional, right? So let's prob. If I just write next prob, print next prob. Oh, it's this. Okay. Okay. Okay, let me just change S0 once. S0 is this. That is P next. PSXS is this. Mm, okay, wait. Let me print these two. Okay. So why this is an tuple? Wait. S is next, comma. So why it become like this? Or let's name it differently. Transition MRP. Still, it is if I just do not do this. I have to restart it. Restart the kernel. ISNP. What is the issue? Next probability it is an array. Next index from the state space, we are choosing the next index. So is there any nope, there is no problem as such here. It is working fine. There is some comma or something that I have placed somewhere which break this. Okay, so this is keep the previous one. Oh, here there is this comma that I forgot to remove. It's fine. We just move back to the previous implementation. Yeah, again there is some comma or something. Oh, comma RWD. Yeah. So you see, the state transition are similar as Markov process. Now you have associated rewards with each state. So basically, whether you get a +1 or you get a -1 from that state or plus some number, and after the entire kind of your trajectory or some after some unveiling up to some timestamps, right? You get a total reward 40. So this is Markov reward process, and the catch is one thing that is important. So there can be this ongoing processes. So these Markov processes are basically never ending. Okay, so they never end. They just transition to one and after like consecutive states, right? But there can be processes which has a terminal state. So those are known as finite like Markov random processes or Markov reward processes like this. So within the state space, there is this starting state S0. There can be a terminal state ST also. After reaching that state, the 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 process get closed. Okay, but you just restart. So it's more evident in a game scenario. So games are basically Markov descent process, right? So you always have a win state or a lose state, right? After playing for some time, you would either win or you would lose, right? After reaching some state, maybe the state is dependent on how many moves you make. So let's say I make 100 moves, my game ended. So whichever state I am at the last 100th move, that is my terminal state. So that is more kind of uh, evident for a game or Markov descent process, but it can be also applied to, let's say, Markov reward processes. Okay. So here the ending state is the 10th state. Okay, I can also unroll to, let's say, 100 transitions, and my unroll would look like this. My entire reward accumulation at after 100 unroll would be 223. So there are like multiple kind of very crucial theoretical things. So for example, so we'll make cover these things later on. Okay, so these are important for building up for, let's say, MDPs or these TD learning concepts. There is a concept called return, right? Return, and return is nothing but total reward that you get from a state to the end. This is what return is. So let's say I am at state 4, okay, and from state 4 till state terminal, say state 100, whatever reward I accumulate, right, the total reward, that is the kind of return of state 4, only state 4. So this 223, what is the return, like which state has return of 223 in this case? The state 0, right, because it starts with state 0. So my state 0 has a return of 223 in this entire trajectory. Now if I just roll again, right, see my return has changed, right? Now if I roll again, right, so my return has changed for the state 0. So how many values we observe? Initially we have 223, next unroll we have 280, third unroll we have 367. Again, if I just roll again, right, 261, right, and these are all for state. So return of RET, return of state 0, right? These are all possible kind of values for 4 runs. So now there is a concept of value. Value is basically average return. Value of S0 is basically your, I will explain it more in more detail in the following classes. Average return from S0. So what is the average at this point after 4 runs? If I just take a mean of this NP, yeah, this, right. So my value for state 0 would be this. Similarly, if I just compute returns for state 1, return for state 2, that would be computed in a similar manner. So because I always start with state 0, I can easily compute the return, total reward or return, by just looking at the total reward, right? But similarly, we can also compute for state 0, state 1, and state 2. Okay, and so see, goodness of a state is basically characterized by 3 things, and that is like actually depends on in which perspective you see the state, whether you are in a greedy approach or whether you are seeing in a long term kind of planned approach. Okay, so if you just see the reward at that state, right? Reward at S, reward at ST, right? Three things: goodness of a state, you can see the reward. So in our case, state 0 has reward -1, state 1 has reward 10, and state 2 has reward 2. Okay, so you can see the reward, you can see its return. So return is basically return in one sample of the transition, how much total reward you get from that state, right? So you can also see return at that particular state of a particular episode, right? So these are known as episodes, okay, of a particular. So return is also kind of at episode wise. So E1 or En, nth episode you get the return of a state, and also you can take the value of a state. So value is what? Average return you get from multiple episodes, right? So see, this reward is kind of a greedy choice. Okay, you just took the immediate reward you get. Return is basically kind of uh, uh, total reward from that state. If I just take it here, total reward from that state to the end at episode En. So it's not that much greedy, but it's still not mature enough, right? So it's like kind of still, it can still fluctuate, right? So in the next episode, it might change. Okay, so basically this is entirely greedy. So you do not have any notion of planning, right? You don't plan for future. You just characterize a state by just looking at the associated reward. But return gives you a futuristic view, but it's still very noisy. And value is basically average return from multiple episodes. That is kind of an good like uh, that you can say uh, normalized estimate of a of goodness. Okay, so how good is the state in terms of future returns? Okay, average future returns. So these are the kind of three key concepts that we'll cover. So later on, there is this concept of Q values and all. So those are called state action values. Okay, so we'll cover them later on, maybe in the next class. So in the next class, maybe we'll cover this Markov decision process and this concept of Q table and some kind of algorithmic algorithms that are there on these type of things. And by the way, this entire part is known as, because we are building the kind of model of the environment. This entire part is called model based. Okay, model based. All right. So you are basically building the model for the algorithms. Okay, you know the model of the environment. So you know all the transition probability matrices, or the what are the possible states there. Let's say if there are actions, right? You know all the actions possible, just like a grid world, right? Just like this repository, you know all the possible states, you know all possible actions that you can take. Now, what is the plan that you can produce to reach to this cake, right? That those algorithms we will cover next. Okay, after those algorithms, there are like other reinforcement algorithm that doesn't need to know the world or doesn't need to know the transition probability matrix or anything. It's very hard, right? So to build transition probability matrix of a real world system is very hard, right? So if I am just walking through wet tiles, what is the probability of me getting uh, uh, like fall down in the floor? That's not computable, right? So in most cases, we don't have this type of model of the world. we don't have these transition probability matrices. So reinforcement learning in like up beyond this model based reinforcement learning, there are methods that basically samples from the world or basically play from the world to learn policies, so to learn how to behave optimally in the environment. Okay, so before that you have to know this type of concepts, so return, reward and value. Okay, so next day we'll go with MDP and then some algorithms with the knowledge of the world. So on MDP is how we can plan, okay, plan our actions to the target or the let's say goal state. So in case of MDPs, we have goal state also. So for example, here, right, these are goal states and these are terminal states. So if you just fall in a hole, you just die. Okay, so these are terminal states. This is the goal state. So we have to plan our path to the goal state. Okay. Okay. So I guess we can close our discussion today. You have any questions? I'll share the notes maybe for the reinforcement learning part. I will share my notes also, which I follow earlier. Okay, in the same drive folder. Any questions, guys? Okay, so not so. Just let me know if you have any questions in the WhatsApp or you can reach me over email. Okay. S- Stop recording. Stop recording. Okay.